Hello. You'll be delighted to see what we have built here in the Orchestrator project. As the team, we have myself, Russell, and Kevin as researchers, and we have James and Will as our faculty members. The Heliolab vision is to reframe AI and data from point solutions to network intelligence. We can orchestrate AI products like Lego to make a full picture of the solar environment. Wouldn't it be helpful if we can orchestrate AI methods, like all of the awesome FDL projects, as easily as saying tea, Earl Grey, hot? Well, that's exactly what we're trying to do. Introducing Heliolab Orchestrator, an agentic orchestration engine for heliophysics queries in natural language. We can ask in natural language for simulations of active regions of the sun from the Arcade project. It orchestrates, and it gives the results of the Arcade team's models. We also just saw the presentation from the ionosphere team. How about a calculation of the electron density profile in the ionosphere under the IRI model? Once again, it orchestrates, and voila, the electron density profile. But how does it actually build these beautiful Lego creations? Stay tuned to find out. Let's examine an example where we asked it to create a data pipeline for model training. After some back and forth for clarification and an approval request to actually go ahead and create the infrastructure, it produces the pipeline. This is the instruction manual for the pipeline it created. It includes infrastructure and code for downloading and calibrating data, as well as model training and evaluation. A human in the loop is required for granting approvals. But who creates this instruction manual? Why, the master builders, of course. We have the new master builder approach to systematic research, which is our mechanism that we wish to measure. And then we have the new master builder reasoning with a star benchmark dataset, our yardstick. How does this new master builder approach to systematic research work? The master builder unlocks the potential of Google ADK for science, with agents and sub-agents in different agentic design patterns optimized for specific purposes. Supporting these agents, the master builder has MCP servers, including a super gateway bridge server and extension tools. To communicate with the master builder and access the system, we have a natural language UI and transparent logging. To that end, this is the Orchestrator's web interface. In the center, we have the chat window, showing prompts, agent replies, and local tool activity in real time. Below that, we have the infrastructure monitor, depicting the infrastructure created, giving warnings about possible memory and credit overloads, as well as system logs. On the left, we have the session list, where each run is tracked with a unique ID, and switching between sessions is easy. And on the right, we have we keep a record of approvals and system events, so the human always stays in the loop. Now that this system is available, how do we know that we're navigating around it well? Do we have the right yardstick? I'll pass the mic to Kevin here to discuss this master builder.
So the whole field is learning a treasure trove of design pattern, but not yet for heliophysics, that calls us to create a reasoning with a star dataset. Our answer is to bring this new type of agentic reasoning to space science. Surprisingly, we discovered a way to use NASA's Living with a Star program problem sets for the heliophysics summer school for LLM reasoning. It consists of heliophysics questions and answers in PDF files across different topics, and we convert these files into JSON lines format in our Reasoning with a Star dataset for LLM reasoning input. We can use Orchestrator to decompose a query, assign expert agents, and log each step. But we also need a way to evaluate these approaches for science domains systematically. It's heliophysics for AI, both guiding Orchestrator and giving us a way to measure our agent development progress. And since we have created the dataset, how do we benchmark it with different agentic architecture with a query in our Orchestrator chat? That brings us to here. We turn a bunch of agentic design into a dependable system. For the heliophysics benchmark use case, Orchestrator prepares a dataset for two agentic design patterns. For example, the first pattern uses a cooperative workflow through physics-aware and math-aware experts to inform the summarizing agent. And the second pattern uses the hierarchical workflow from the higher to lower hierarchy throughout the process. Both patterns will return their answers. And the system scores the output based on the accuracy, latency, and resource usage for the comprehensive report. This allows the system to learn which pattern works better, so it can select the most suitable architecture next time. And we created 4-agent architecture. Here's one architecture we named PACE. This is a simple design pattern which solves a query through plan, answer, critics, and enclose. Each task is broken down into smaller plans with acceptance check. If the system does not pass the acceptance check, it will return to the solver one time before the system outputs the final answer. Other architectures also employ similar ideas. For the multi-agent patterns we design, some are able to do self-refinement and allocate domain experts. However, we'll go through them in detail at the technical showcase. We compare our agent architecture across 3 domains: math, science, programming, with 6 datasets. We evaluate our architecture with Google's Gemini 2.5 Pro. In the mathematical datasets, all design patterns converge, with PACE marginally more performant, at least compared to more complex architectures, i.e. GSM-AK and math. This means simpler architecture is enough. And for GPQA, the PhD level problem sets in physics, chemistry, and biology, faces hypothesis generation capability helps improve the chain of thought in the reasoning task. In human eval and SW bench, performance varies by the coding task type and by agentic architecture complexity. Now we want to check this architecture against our heliophysics dataset, reasoning with a star. And this is where, all without retrieval of domain-specific knowledge, what James said about an agent's ability to Google things, which you expect to boost these results. Analytic design, especially schema and phase, perform better with the unfamiliar heliophysics query. We also conducted performance analysis on reasoning with a star based on the heliophysics and math categories of each problem set. We're excited to share these in the upcoming technical showcase. And summarizing the result, there's no one-size-fits-all design pattern. Our orchestrator should choose the design pattern to match the task.
With the Orchestrator system, we can compose other machine learning models, physics simulations, and data pipelines that previously took weeks, months, or even years into just minutes to prototype. This significantly helps scientists focus on the research aspects instead of the technical toolings for space research and operations, while keeping humans in the loop to verify the augmented process. Heliolab Orchestrator, the future of scientific discovery. Thank you.